The fact that light takes time to travel through space has important implications to our observations of the universe, because it means we are always looking into the past. Consider Alpha Centauri, the nearest star system to our own. Because it is about 4 light years away, meaning that its light takes about 4 years to reach us, we see it not as it is today, but as it was about 4 years ago. The effect is more dramatic at greater distances. The beautiful Orion Nebula is about 1,350 light-years away, which means we see it as it looked about 1,350 years ago. If any major events have occurred in the Orion Nebula since that time, we cannot yet know about them. The general idea that light takes time to travel through space leads to a remarkable fact. The farther away we look in distance, the further back we look in time. Here we see the Andromeda Galaxy, whose 2.5 million light-year distance means we see it as it looked 2.5 million years ago. Notice that this means our telescopes act somewhat like time machines. When we look to great distances, we see objects as they were in the distant past, when the universe was much younger than it is today. For example, the first galaxy in this diagram is labeled as 7 billion light-years away, by which we mean that its light has traveled through space for 7 billion years to reach us. Therefore, we are seeing this galaxy as it was 7 billion years ago, when the universe was about half its current age of 14 billion years. Light from a galaxy 12 billion light-years away took 12 billion years to reach us, so we are seeing that galaxy as it was 12 billion years ago. Because the universe is about 14 billion years old, this means we are seeing the galaxy as it looked when the universe was only about 2 billion years old. Now consider this question. Suppose we observe a supernova located in a galaxy 10 billion light-years away. How old was the universe when the supernova occurred? Was it 1 billion, 4 billion, 10 billion, or 14 billion years old? The answer is B, 4 billion years old. To see why, remember that the 10 billion light-year distance to the supernova means it occurred 10 billion years ago. Because the universe is about 14 billion years old, a supernova that occurred 10 billion years ago happened at a time when the universe was about 4 billion years old. Notice that if we look to a distance with a light travel time equal to the age of the universe, or a distance of about 14 billion light-years, we are looking back to the time when the universe was born in the Big Bang. In fact, as you'll learn later, astronomers can see nearly this far, and the light they have detected from shortly after the Big Bang is known as the cosmic microwave background. These ideas put a limit on the portion of the universe that we can observe. To see why, imagine that we tried to look to an object at a distance beyond 14 billion light-years. Because the light from this object needs more than 14 billion years to reach us, the universe has not yet been around long enough for this light to have arrived. A distance of about 14 billion light-years therefore defines the boundary of our observable universe, the portion of the universe that we can in principle observe. Note that this fact does not put any limit on the size of the entire universe, which we assume to be far larger than our observable universe. We simply cannot see or study anything beyond the bounds of our observable universe. In other words, the boundary or horizon of our observable universe is a boundary in time, not space, because the light from objects beyond this horizon has not yet had time to reach us in a 14 billion year old universe. There is one important subtlety that we have not yet discussed, and it arises from the fact that we live in an expanding universe, which means that very distant galaxies are moving away from us, even as their light travels toward us. This introduces ambiguity to the word distance, because it is not obvious whether we mean the distance now, the distance when the light left, or the distance at some other time in between. In stating distances like 7, 12, or 14 billion light-years, we have been basing it on what astronomers call the lookback time, which is the actual time it took an object's light to reach us. In other words, when we say that a galaxy is 7 billion light-years away, we mean that it has a lookback time of 7 billion years, so that its light actually took 7 billion years to reach us. In this textbook, you can always assume that distances stated in light-years are based on lookback times.